Good morning on this first missed day of school. I believe it's because of flooding. So, but this exact scenario right here is why we do the flipped classroom because we can keep going, not get any days behind, and we'll be able to stay on time for the exam. As you can probably tell, I've decided to do this outside. Mostly because it's a nice cool day, but I also need a break from my kids. So, anyways, um, we're going to go ahead and get started. This is a lesson that I did last year in class. This was so I did the intro in class and then had them watch the video that night. So, but you all are not going to have that luxury. You're going to get the both videos today. The intro video, which is what this is, and then video one, which is on neurons. So, but we're ready to move on. This unit is fairly difficult just for the fact there's just so much stuff. I mean, we are talking about the brain and how it works and neurotransmitters and things like that. So, after this unit, then things really kind of get smooth out and we start getting into more interesting stuff. But if you can hang through this unit here, then we'll be good to go. I know some of you have still not taken the assessment because you weren't here on Friday. You will do that the first day back. So I'm guessing that's going to be tomorrow on Tuesday. But anyways, we're going to go ahead and get rolling. This right here is something to. Let's see if I can use this. Yeah. Let's do a laser pointer just because. All right, this right here is something that is a term that I've probably failed to mention more often than not. This is, we've at the beginning of the year we, excuse me, we talked about a lot, all the different psychological perspectives, all right, and how we're going to pretty much hit each one throughout the class. Well, this is one of the first ones we're hitting, and it's the biological perspective. So, in the biological perspective, people will say this constantly: everything psychological is simultaneously biological. So, before we get started, you will have a watch guide to complete. So if you haven't already seen that, I'd go ahead and find that and get that ready so you can fill that out as you're watching the video. Because this right here is probably going to be the very first question, something along those lines. So just giving you all a heads up. Anyway, excuse me. I'm still not feeling great, so maybe I need some fresh air. Anyways, to think, feel, or act without a body would be like running without a legs. Biological people say that we are biopsychosocial systems. And to understand our behavior, we need to study how biological, psychological, and social systems interact. So, where and how do all these things mesh together? The human brain is the most complex system, natural or man-made, in the world. Brain weighs about 3 pounds and is generally about the size of a grapefruit. Last year I had a grapefruit, but with some of the medicine I'm taking now, I can't have grapefruit, which I don't really like anyways. But there you go. I don't have a grapefruit to show you. It's pinkish and gray in color, and it contains about 100 billion nerve cells. And that even at a loss of 200,000 neurons per day during our adult lives, we still end up with over 98% of our brain cells. So, and here's an actual picture of some nerve cells and some synapses, which we'll talk about here in a little bit. But just basic stuff about your brain. Again, typical brain contains about 100 billion neurons. It does consume about a quarter of your body's oxygen. So every breath you take, a quarter of that is going to fire your brain. And when we lose oxygen, and I'm going to show you some videos of that here in a minute, funky things happen to us in our brains. When people have heart attacks, generally the problem that is associated with that is actually more the brain, and that the brain doesn't get the oxygen that it needs to do what it needs to do to keep the body alive. Um, when the heart, and I know this personally, when the heart is not pumping correctly and getting enough with not enough power to shoot the blood where it needs to go, which contains the oxygen, bad things happen. So the brain also spends most of the body's calories. Believe it or not, I don't know what kind of diet that is, if that's a standard 2,000 calorie diet or whatever. But so the brain uses a quarter of our oxygen and most of the body's calories. That's why I don't mind you all eating in class, because you all need those calories for your brain cells. Brain is 70% water and weighs about 3 pounds. You all have probably heard of the rule of 3. This is generally speaking that our bodies can tolerate 3 minutes without oxygen and before we start getting neurological damage. 3 days without water before we start getting dehydration problems and organs start shutting down. And 3 weeks without food. It's one of the reasons why I like the show Alone on the History Channel. Because it puts at least this one, you don't normally see this one put to the test as much, but it's a good show. There are, excuse me, there are rare exceptions. The resuscitation of a 2.5-year-old girl who was submerged in an icy creek for more than an hour is one of the rare cases that even the Journal of the American Medical Association describes as miraculous. 2 years after doctors in Salt Lake City revived Michelle Funk, she is bright, perky, and growing up normally. The 66 minutes Michelle spent in the creek is the longest documented submersion with an intact neurological income, meaning that poor girl was underwater in an icy creek for 66 minutes. And as of now, or as of whenever this PowerPoint was put together a couple years ago, she is still growing up fairly normally. So there was no issues with being in the icy creek. So that's helps. And it looks like breakfast is ready. Let me do one more slide. So watch what happens when oxygen is deprived from the brain because of excessive G forces. These are pretty funny, I think. Let's go back to automatic. There we go. All right, so this is a G-force generator. At the certain G's, oxygen actually kind of separates out from the blood a little bit, and it no longer feeds the brain like it's supposed to. Now here's your G-forces 7, 7, 6. They keep him there, and he's out. Watch him wake up. Here, we'll do that again just because I think it's funny. 7.6 is generally the point where he passes out. He's breathing, and he's gone. Of course, his hand is on the stick still. If he was in a fighter jet, he'd be going straight down. He's trying to wake up back to 1, and then he loses everything and starts flailing around. And he remembers where he is now. That's what G-forces do. Now, it's going to be different in everybody. You all have been on one of these before, these slingshots. Looks like this person's already out. Yeah, that one's all right. I'm gonna go have breakfast, and then I will return shortly for this one because this is an interesting one. This one has this is from the BBC and has shows what happens when oxygen deprivation happens at a slower rate. So pause. All right, I am back. It was a good breakfast of waffles and bacon. So what I've got here is a video. It's a few minutes long, but it is a British pilot who is basically going to be shown through the effects of a slower oxygen deprivation. He's in a oxygen deprivation chamber, and you'll see what happens when your brain doesn't get the oxygen that it needs. Whoa, that's not it. Go back. All right, I've had to adjust this video because after I posted it, I guess it was copyright flagged for this little clip I'm trying to show right now. So I've just went ahead and cut the clip out, and then I'm going to repost this video with this in here. Sorry for the interruption. Those of you who tried to view the first one said I couldn't. I got a couple emails, and I appreciate that. So we're trying to get it taken care of, and so now you can continue watching. We'll probably watch this video because I think it's interesting on Tuesday. So anyways, peace out. Sorry for the interruption. All right, pretty intense way of showing what oxygen deprivation can do to the brain. And then here's a fighter pilot. There's one more example. It's just a fun video to show of the effects of lack of oxygen on the brain. And he's out. All right. So, here we go with the math thing. More math, just not as much as the last unit. But, so we've got 100 billion neurons in 10 trillion cells, and one neuron equals 100 body cells. It's more or less. 100 billion neurons, 200 million spinal cells, 0.02% of the brain size. I'm going to go forward because this is boring, and I don't think you're going to be asked this on the exam. All right, there's where we are. The neurons. Neurons cluster into work groups called neural networks. So the neurons that deal with sight, for instance, are called like a vision. They're a vision neural network. The ones that deal with motor skills is a motor neural network. So all these neurons that cluster into different groups and they talk to different cells and turn on and turn off and all that are all part of specific neural networks. To understand why this happens, think about why cities exist and how they work. You've got interstates coming in. Think of a neural signal as products on a truck. The truck comes in, the product comes in, hits a warehouse. Then it maybe gets on another truck and goes to a store. Maybe it gets on a train and goes to another warehouse. We'll do that, and then maybe it goes on to the next one and goes to another warehouse, in which case it's then sent to the store, and in which case we buy it. There's a lot of different pathways for things to go from each of these initial neurons. Neurons work with those close by to ensure short, fast connections. And here's an example of neural messages being transferred from an initial something to the end. As you can see, some of them are moving very, very fast. Some of them are not quite as fast, but it's almost like lightning. It's about as quick, especially look down in this area here. You can see a lot of them shooting this way, basically at the speed of light or the speed of lightning. It's how fast those things move. I'm going to skip this video for now. I'm going to post this PowerPoint online. I would suggest go back and looking at it, but I think the last time I posted this, I got hit with copyright infringement, I think, for this video. So I'm going to leave it off. I would suggest go back and watching it. It's about 4 minutes long. So yeah, it looks blank, or maybe it's got a slight. It shows you how that a researcher is creating 1 millimeter slices of the brain on film, and then putting it onto a almost like a projector, and it shows not the brain, not necessarily through time, but through space. It's a 3D model, so it's almost like you're moving into the cell. It's kind of neat. And then they do a computer mapping. It's a neat little 5-minute video. I'd suggest watching it. All right, so our body's communication. Internally, there are 2 communication systems. One works very quickly, and that's called the nervous system, and one works very slowly, or not very slowly, but slower, called the endocrine system. You know, the nervous system deals with things like your brain, your cerebellum, spinal cord, and all your nerves. You know, the things that are that shoot those neurological impulses real quick. The other system, the endocrine system, that's a bit slower. That uses, instead of using electrical impulses like the nervous system does, it uses chemicals. Thyroid, pituitary gland, ovaries, testes, pineal gland. All these are glands that secrete chemicals that they send the message, but it's a bit slower than the nervous system. So the content objective for this unit is you need to be able to use these words pretty regularly and know what they mean. We'll get more into these as we go through the class, but you know, neuron, which we've talked about, is basically a brain cell. Dendrites we'll talk about I think tonight. Axon, synapse, myelin sheath, terminal buttons, neurotransmitter, absolute threshold, action potential, all or none principle, plasticity, reflex, neural pathway, agonist, and antagonist. These are all things you're going to need to know about when we take the test. There are 3 types of neurons. While they can be different sizes and shapes, they all share a similar structure and function in a similar way. They are broken into 3 categories based on their location and function. Sensory neurons obviously deal with senses, and we'll talk more about these here in a minute. Motor neurons and interneurons. Sensory neurons, also known as afferent neurons. You'll actually see both terms on the exam. So make sure you know both terms, but they're essentially one-way streets that carry traffic from the sense organs towards the brain. So things like your skin, your vision, hearing, taste, smell, balance, and all that stuff. Those are sensory neurons because that's how we sense the world, and that information all goes one way, goes straight up toward the brain. All right. And that's kind of one way to remember all this stuff is that, all the sensory neurons carry basically the senses information from wherever they get the sense to the brain. Motor neurons, or efferent neurons, are one-way streets that go from the brain to the muscles, organs, and glands. So Sensory goes into the brain, motor neurons go out of the brain. Is an easy way to remember that. They transport messages away from the brain to the muscles, organs, and glands. Again, that all so they can get those messages they need to get. You know, if you look up and your sensory neurons sense a large bear running at you, that will be sent to your brain, transcribed into something useful, and then the motor neurons will be sent to your muscles, telling you to get the you-know-what out of there. Sensory and motor neurons do not communicate directly with each other. Instead, they rely on a middleman, and that middleman are those middlemen people or cells are called interneurons. These make up the majority of our neurons, believe it or not. They relay messages from sensory neurons to other interneurons or motor neurons in the complex pathways. So the sensory neuron is actually what senses it, and then the interneurons are what sends it. They're like the highway. And then vice versa. The motor neurons is what sends and what receives, and the interneurons are the ones that's in between the brain and your muscles or whatever's being moved. And that's what we're going to end with today. Be aware. Make sure you look for the watch guide and have that completed by tomorrow morning whenever we have class. And there will probably be one also for the one you're supposed to watch tonight, the Neuron 1 video. So hope everything's all right. Now, that video is from last year, so there may be some allusions to some stuff from last year's class. But anyways, hope you all are having a good day. Stay dry, stay safe, and I'll see you all later. Peace out.